This diagram shows a string of 8 zeros. To verify that 8 is a power of 2, we can repeatedly cut the string in half. We cross out every other 0, reducing the count to 4, then 2. If the process finishes with exactly 1 0 left, the number is a power of 2. Starting with 6 zeros produces a different result. We cut it in half once, leaving 3. Because we cannot divide 3 zeros evenly, the process stops. Any number that is not a true power of 2 eventually encounters an odd number and fails. This is our formal problem definition. We need to construct a Turing machine that accepts a string of zeros only if its length is a power of 2. Note the typo in the original text. It reads power of 1, but the logic clearly requires a power of 2. Translating this halving logic to a physical tape requires a repeating routine. The machine will sweep from left to right, cross out exactly half of the zeros, rewind to the start, and begin the next pass. A Turing machine operates as a physical engine, solving mathematical problems through the spatial manipulation of symbols on a tape. Starting at state Q0, the machine reads the first 0 and replaces it with a blank B before moving right. This B acts as a physical left wall. When the machine rewinds for another pass, this marker signals exactly where the tape begins. The Q1, Q2, Q3 triangle is the halving engine. Entering Q1, the machine overwrites a 0, transitioning to Q2. From Q2, it leaves the next 0 unchanged, moving to Q3, where it crosses out the following 0. This loop crosses out every second 0. Self-loops on Q2 and Q3 allow the head to bypass X marks, ignoring previously crossed-out positions. This triangular arrangement functions as a mechanical parity checker, using a toggle mechanism to solve the division problem. Consider the state when the head hits the blank space on the far right. If the machine is in state Q2, was the total number of zeros even or odd? It was even. Because the machine enters Q2 immediately after crossing out a 0, hitting the end of the tape proves every 0 had a pair. The diagram maps this success condition through Q4. Upon reading the right side blank, state Q2 moves the head left until it reaches the initial boundary, returning to Q1. Now look at Q3. The machine arrives here after skipping a 0. If the head hits the blank end, the count was odd. Notice there is no transition arrow at Q3 for a blank. This is a case of implicit rejection. If a Turing machine encounters a symbol and has no defined instruction for what to do next, the machine crashes and halts. Omitting paths for odd parity ensures the machine's physical structure automatically filters out incorrect strings. Eventually, after multiple passes, only X marks remain. The machine enters Q1, scanning the string. With no zeros left to trigger a state change, it scans right through the X marks. Reaching the final blank proves the original string divided perfectly to 1. On the diagram, state Q1 reads the final blank, transitioning to QF. This double circle is the accept state, confirming a power of 2. The whole machine has 3 zones: the Q0 boundary setup, the Q123 halving engine, and the Q4 rewind track. Modeling exponentially growing numerical sets is achieved by combining simple, modular components, like boundary markers, toggle switches, and rewind loops, into a